Welcome back to this lecture series on pulse width modulation for power electronic converters. Now, we have been discussing power electronic converters for quite a while now over the last 4 lectures, and this is probably going to be the 5th lecture. Now, as we discussed earlier, power electronics involves control, conditioning and conversion of electric power. Electric power might be available in the form of a DC or AC of a particular frequency and an amplitude. You might want AC voltage or DC voltage of another amplitude, of AC of some other frequency. So, we need electric power conversion because many times the load that we have might have a different power supply requirement from what is available. Like that is what we have been discussing all through. We may have a 230 volt 50 hertz mains available, but the load might need 110 volt DC. So, you need rectification. You might have a 400 volt 50 hertz 3 phase AC available, but your motor induction motor might need a 200 volt 250 hertz supply voltage. So, in such kind of situations you need conversion is required, and that is why we have power electronic converters now. And here the conversion is primarily done based on switches. So, first we discussed about various switches, electronic switches like various semiconductor devices such as diodes, thyristors, IGBTs, MOSFETs, etc., which can act as switches. Then we went on to converters. How do you use switches to do a DC to DC conversion now? From DC to DC conversion, we moved on to DC to AC conversion, and in DC to AC conversion we looked at voltage source inverters and current source inverters. I mean DC could be available either as a voltage source or current source. So, depending on that you might need a voltage source inverter or a current source inverter. So, we discuss both possibilities now. Then in DC to AC conversion we have been moving to another step which is called multi-level converters, and we discussed multi-level converters, some aspects of multi-level converters last time, and we are going to continue this. This is the second lecture on multi-level converters now. So, let us take a look at what is a conventional 2-level voltage source inverter. This is the standard 3-phase 2-level voltage source inverter. I would call this as a 2-level voltage source inverter because of one reason. I would call this as a 2-level voltage source. Why? If I have my all these are single pole double throw switches, let me consider this point R, which is a pole, which is the midpoint of a leg. This VR measured with respect to the DC bus neutral O can only take two values here, either plus VDC by 2 or minus VDC by 2. Hence, we call this as a 2-level voltage source inverter. Now, in this case all these are, so R is connected either to the positive bus or negative bus through a single pole double throw switches. For every leg you have a single pole double throw switch, and these 3 poles are connected to the loads, and the loads are presumed to be inductive here. An inductance current through an inductive circuit should never be opened, you should always provide path for it to flow through. Therefore, the load terminals are connected to the poles, and the pole is going to be connected either to one throw or the other throw, and so, therefore, there is a path is always going to be available here now. And as was also remarked earlier, this is really a bidirectional power converter. Power can actually flow in both the directions. It is not necessary that needs to flow from the DC side to the AC side. You have a DC supply here, let us say current can be flowing like this, and here this is be DC, and this can be DC plus ripple flowing like this. Let me call this as IDC, let me call this as some IDC plus I tilde, certain ripple current. I will also call it I tilde DC just to say that it is on the DC side now. So, what we are going to see is and the ripple is flowing through the capacitance. Now, the power flow is in which direction? It is from the DC side to the AC side, that is what it means now. And here again you would see the power factor on the load side. If you look at the fundamental voltage and the fundamental current, they will be close to one another, their phase will be close to 0 or within 90 degrees plus or minus, and therefore, the power is flowing in the opposite direction, in one direction from DC to AC. Can power flow in the opposite direction? Of course, power can also flow in the opposite direction if you make sure that this IDC is now in the opposite direction. If you say this IDC is in the opposite direction, and if you look at the phase relationship here, the voltage and current could have a phase difference of 180 degrees, let us say, instead of 0 degrees. So, that basically means power is flowing in the opposite direction. It is actually a bidirectional converter, power can flow in either direction, that is the point that I would like to make now. and this is called a voltage source inverter because you can apply certain voltage at this pole irrespective of the direction of current that is flowing through. The current can be in both the directions. This is what we took into account while designing the switches. What did we do? We realized a single pole double throw switch using two such IGBTs. These are capable of conducting in both the directions. So, and when this is conducting like this will be blocking a potential, the lower transistor will be blocking a potential equal to the DC bus voltage with polarity as shown here. The same way when the bottom is conducting and the top is turned off. So, it depends on whichever direction the load current flows. Depending on the direction of load current, it is either the transistor or the diode which is going to conduct now. So, this is how you realize a single pole double throw switch. If you call one of them as SR and if you call the bottom as SR bar. So, these two are actually switched in a complementary fashion. If the top is on, the bottom is off and vice versa. So, it is a single pole double throw switch now, and R can take either plus 0.5 VDC or minus 0.5 VDC with respect to O. Similarly, Y can take either plus 0.5 VDC or minus 0.5 VDC with respect to O. The difference between R and Y can be either plus VDC or 0 or minus VDC. That is what we have. Now, we want to see whether between R and Y we can have only plus VDC, 0 and minus VDC. Why not have plus or minus 0.5 VDC for example. So, that is if you want to do something like that, then you need what we call as a 3 level voltage source inverter. A 2 level is what we saw before and a 3 level is now what we are going to look at, right. So, now this is the 2 level voltage source inverter where every leg is a single pole double throw switch. Now, it is all a single pole double throw switch. There are 2 throws here. If you look at the lower picture, there are 3 throws here. There are 3 throws. As before, the load is presumed to be inductive and therefore, the load terminals are connected to the poles. The poles are always connected to one throw or the other. Therefore, there will always be some path available for the load current to flow through. Now, what we have is R, this pole can be connected to, let us say, the positive throw plus, or it can be connected to the middle throw 0 or it can be connected to the bottom throw minus. Earlier, it could be connected only to the positive DC bus terminal or the negative DC bus terminal. Here it could not be connected to the DC bus midpoint. Now, we are able to connect it to the DC bus midpoint also. So, we use a single pole triple throw switch and the third pole or the middle pole is used for doing that now. So, this is a 3 level voltage source inverter. Whenever you are talking of a 3 level, 4 level or anything 3 or above, we call it by the generic name multi-level voltage source inverter now. Generally, we would be in this course by and large when we say multi-level inverter, we would mean a 3 level inverter. It is also possible for you to have a single pole 4 throw switch, for example, 4 different voltage potentials here instead of 3 potentials plus 0 and minus, it is possible to have 4 different potentials and have a single pole 4 throw switch. Similarly, in the DC it is possible to have 5 different potentials and have a single pole 5 throw switch. So, this would be called 4 level inverter and 5 level inverter and so on. So, all these are multi-level inverters, but we in this course when we say multi-level inverter, we usually mean a 3 level inverter. That is true even otherwise. So, now we look at we in fact already looked at how do we realize this single pole triple throw switch. So, now before that we just wanted to see why a 3 level inverter, just to reinstate our idea now that is the concepts. Now, R need not be just connected to plus or minus, it can be connected to 0 also. Similarly, if you look at the potential between R and Y, for example, V or Y can take either plus VDC or minus VDC as in a 2 level inverter. It can also take either plus VDC or minus VDC by 2 besides 0. These are all the various values that it can take. In a 2 level inverter, it is only plus or minus VDC or 0. In a 3 level inverter, this one is extra. It can be plus or minus VDC by 2 also. So, there are more number of voltage levels available at the output and therefore, it is possible for you to follow a sinusoidal waveform better. See, what you ideally want at the output is a sinusoidal waveform, you are never going to get that now, because we are using DC and we are trying to produce AC out of DC. So, there is going to be always some amount of non-sinusoidal components, it is going to be distorted now. We want to move closer. So, one way is if the voltage levels, this provides you certain additional voltage levels or intermediate voltage levels, so that you can follow a sine voltage waveform better. We will discuss more of this later. Now, another important reason why you want is your DC bus voltage may be high. In India, we have 3-phase motors which are typically rated something like 400 volts to 440 volts RMS line to line. Now, in some other countries it could be 110 volts or 208 volts or whatever. We may also have, when you go to higher and higher power levels, the motor voltage rating may also be higher. It could be higher than a kV, for example, it can be a few kilovolts. So, such motors are called medium voltage motors, and to drive a medium voltage motor you might need an inverter. In such a kind of a scenario, what you will have is, a 3-level inverter or a multi-level inverter is quite useful here. Now, you will have a higher DC bus voltage because your motor voltage is now higher, and therefore, correspondingly you also need a higher DC bus voltage now. If you have a higher DC bus voltage, you need switches which can block so much of DC voltage whenever they are in off state. You need switches whose voltage ratings are substantially higher than whatever DC voltage that you use now. If your DC voltage is something like, let us say, about 3 kilovolts or 5 kilovolts or 6 kilovolts, it will not be possible for you to have, you may not have devices to do this now. So, in one thing that you might do is go in for series connection of devices, so that you can match the required voltage rating, but better than going for series connection is such a multi-level configuration now. So, this is again something that we will see a little later. So, here you need only devices of voltage ratings VDC by 2, as we will see shortly. So, these are the two primary reasons, I mean, to handle higher DC bus voltages and to produce superior waveform quality, output waveforms of superior quality are the two primary reasons why one would probably go for a 3-level inverter. Just basic motivation now. We have been looking at actually how would you realize this switch now. If you want to realize one part of the switch, pole P to throw T1, the 3 different states are available here now. In this first case, pole P is connected to T1 now. So, the current can be bidirectional, therefore, the current between P and T1 needs to be bidirectional now. If you take the second state, the switch between P and T1 or the switches between them are in the off state now, and T1 is positive with respect to P, and you have a potential difference of VDC by 2. You have a potential difference of VDC by 2. If you take the third state, again the switches or the devices between P and T1 are in the off state, and they are blocking a potential. Earlier it was VDC by 2, now the potential is VDC. So, this is what you need now. You need a switch between P and T1 which can conduct in both the directions, and it can block a potential with this polarity as indicated here of with plus and minus of DC bus voltage. I mean the voltage equal to DC bus voltage now. So, if you look at the second pole to throw 3, the story is same. When it is connected between pole and throw 3, you need a bidirectional conduction now. When this pole P is connected to throw T1, P is basically connected to the positive bus, T3 is always connected to the negative bus, and it has to block a potential equal to VDC. Whereas, if you take this case, again the polarity is the same, it is blocking, but the voltage blocked is only VDC by 2, and VDC is higher of these two, right. So, if you take the pole P to the middle throw, then what you have is slightly interesting. Again, when it is on, it has to conduct in either directions because the load current could be in either direction. When it is off and when P and T1 are connected, P is positive and this throw is negative, and the potential coming between the two is VDC by 2. When pole P is connected to throw T3, once again the devices between P and T2 are in the off condition now. But if you look at the potential is the same VDC by 2, but if you look at the polarity, it is now the opposite of what it was. Here the throw is positive with respect to pole, earlier the throw was positive, the pole was positive with respect to pole now. So, what you need between P and T2 is a 4 quadrant switch, this is what we saw in the last lecture, whereas between P and T1 and P and T3, what we need are 2 quadrant switches which can block voltage of one polarity, but conduct in either direction. So, what you can have as a first cut realization is like this now. So, if you look at this, obviously it can conduct in both the direction, the transistor can conduct in this direction and the diode can conduct in this direction when P and T1 are to be connected. In such a scenario, you have the bottom switch, the transistor blocking a potential equal to VDC with polarity as indicated above. Now, what you have is you have T1 connected to P, therefore, P is connected to plus VDC. So, now this is plus VDC by 2 with respect to the midpoint. Now, one of the switches should be blocking here, and this is positive with respect to P is now positive with respect to T2. So, if you take this path, this diode will be blocking, and if you take this path, this transistor will be blocking. This potential equal to VDC by 2 here. This potential is VDC by 2. Correct. Now, if you take, now this is what when P is connected to T1. The story will be similar when P is connected to T3. In that case, the bottom transistor or the diode will conduct depending on the direction of the load current, and the top transistor will be blocking a potential equal to plus minus VDC. And here again you may have a VDC by 2 blocked by the other transistor and the other diode as we observed before. If P and T2 are connected together, let us say P and T2 are connected. So, T1 and T2 are in the off condition. In such a scenario, what you will find is both these will be blocking some potentials equal to VDC by 2, and the direction of current depends on, the conduction depends on this direction of current. If I say this is the direction of current, then the current will flow through this arm. If I say the direction of current is different, like here in the opposite direction, then current would flow through this branch. So, this is what will happen now. So, here the situation is, what we need is, it is not enough if you have a blocking potential of VDC by 2, you need switches which can block up to VDC. So, this is what you still need a higher DC bus voltage rating. What we need to see is, we want to use only switches whose voltage ratings are VDC by 2 basically. So, what we do is we connect two of them in parallel. In this situation, let us say there is a current flowing, it could be in either direction. In that scenario, current can be either flowing through the transistors or through the diodes. We are presuming that P and T1 are now connected, and the bottom devices can be blocking potential of VDC by 2 each like this. Of course, this presumes that the voltage is shared more or less equally, but which need not be the case now. To some extent, a multi-level converters configuration can help, which we will see now. Before we go there, let us try and see whether we need all these transistors. We totally have 6 transistors. Do we need all these transistors is one of the questions that we really want to see now. So, that is where we come to this kind of a realization that can be seen from here. So, let us say P should be connected to T2. This is pole P, this should be connected to the throw T2. In such a case, pole P should not be connected to T1. Pole P should not be connected to T1. How do you ensure that? It can be ensured by having either one of the two top transistors, let me call them as S1 and S2. Both of them could be off, or even one of them could be off. So, it is enough if one of them could be off, and it is enough if S1 alone could be off. So, if it is going to conduct, for example, it is conducting to both these transistors now. So, both the transistors are not actually required to separate this T2 from T1. So, let me say, why not make a connection like this? Let me consider these 2 points, and let me say what happens if I connect these two like this. Nothing, because if P and T2 are to be connected, if S1 is turned off, there will not be any connection between P and T1, only there will be a connection between P and T2, and current will flow either through this diode and this transistor. So, there is no problem, it can conduct like this. Similarly, you can also make a connection like this on the lower side. So, these two transistors can actually be in parallel, or they can be replaced by the same transistor, by a single transistor. So, you do not really need two different transistors, and that is what you have as your usual realization. This one we call as S1, this one we call as S2, this one we call as S3, this one we call as S4. So, S1 and S2 will be on for you to connect this pole P to the top throw. S2 and S3 will be on to connect pole P to the throw T2, and S3 and S4 will be on to connect pole P to throw T3. This is what we said now. So, we have been saying that the waveform quality is better than that of a 2-level inverter. Let us see how. See, what you normally need is this potential are we know this is plus VDC by 2, this potential is 0, this potential is minus VDC by 2. What we normally do with any switching converter is at the pole we realize an average voltage which is somewhere between the voltages of the various throws, correct. When in a case of a DC-DC converter, let us say a buck converter, we realize a pole voltage, average pole voltage which is somewhere between the DC bus voltage and 0. And here similarly we will realize an average pole voltage which is somewhere between the voltages of throw T1 and 0 or throw T2 or between that of throw T2 and throw T3. That is, it can be anywhere between plus VDC by 2 and minus VDC by 2. If pole P is connected to throw T1, I mean we are considering a small interval of time, we are considering let us say a small interval of time. This, what do you mean by small interval? This is much smaller than the fundamental modulating frequency that we are talking about now. In this small interval of time, if pole P is always connected to throw T1, then the average voltage is plus VDC by 2. If it is always connected to throw T3, then the average voltage is minus VDC by 2. If pole P is always connected to throw T2, the average voltage is 0. Now, let us say you have some potential like this, let me call this as 0.25 VDC. If I were to realize this 0.25 VDC using a 2 level inverter, what I would do is I will apply some plus VDC by 2 and for a long time and minus VDC by 2 for a shorter time. This is plus VDC by 2 and this is minus VDC by 2. For roughly 75% of the time, if I apply plus VDC by 2 and minus VDC by 2, I get an average like this. This is the situation in a 2 level inverter. If I consider a 3 level inverter, what I can do is I can apply either plus VDC by 2 or 0. I can apply plus VDC by 2 for half the time and apply 0 for another half the time. So, this will also produce the same average voltage. My 0 is not here actually, please ignore that mistake, this is 0. So, I will apply plus VDC by 2 for half the time and 0 for remaining half the time. So, now what do I get? I end up getting the same average voltage. So, I can get this 0.25 VDC by time averaging of 0.5 VDC and minus 0.5 VDC. I can also get this 0.25 VDC by time averaging of 0.5 VDC and 0, which is better. Time averaging of 0.5 VDC and 0 is better. Why? Because the maximum error that you have between the ideal waveform, which is equal to 0.25 VDC, that is what you want, and the actual waveform, which is what you apply, is now is lower now. So, if you consider this, the error is only so much in a 3 level inverter. Correspondingly, if you had consider a 2 level inverter, the error is substantially higher. So, the instantaneous error between what you want, that is the average voltage, and what you apply, that is the actual instantaneous voltage, is higher in a 2 level inverter and is lower in a 3 level inverter. Therefore, 3 level inverter can actually give you a better waveform quality. So, also as we said voltage sharing is better. Now, the entire DC bus voltage is blocked. When it needs to be blocked, it is not blocked by a single device, but by both the devices, let us say S1 and S2 or the devices S3 and S4. Now, they also contributes to certain amount of voltage sharing. See, S1 and S2, if they are blocking a potential equal to VDC, it is not necessary that they should block equal voltages, they should share the voltage equally. The voltage sharing could certainly be unequal. Now, here let us consider this node. Whenever this node goes below 0, the diode will come into conduction. That will force that this potential stays within VDC by 2. This potential when S1 and S2 are blocking, it will make sure that this potential stays within VDC by 2. It will not let the potential really go above that. So, some kind of check is being exercised on the voltage sharing between these two devices. So, a multi-level converter is better than basically two transistors with connected in series for voltage sharing. So, let us say we move on to this is one leg, this is just one leg of that. If you put two such legs together, let me call these terminals as A and B. So, this becomes a single phase multi-level inverter or a single phase 3 level inverter. it is called a neutral point clamped or a diode clamped inverter, as we mentioned before, because what we mean by the neutral is the DC bus neutral. This DC bus neutral could be connected to the face or the output terminal or the midpoint of a leg. So, you call it neutral point clamping, and you use diodes to do this kind of a clamping. It will, if you may conduct through either through this diode or this diode. So, you call it as a diode clamped inverter too. So, this is the name that it normally goes by. If you want a 3 phase inverter, what you need to have is one more leg like this is necessary. You have a third leg, and the 3 terminals, the load terminals can be connected to the midpoints of the 3 legs R, Y and B. Yes. So, this is now a diode neutral clamped inverter. Now, we are just kind of summarizing a few points and understanding a 3 level neutral point clamped inverter better. NPC is the abbreviation for neutral point clamped inverter. Now, let us say if pole P is connected to throw T1, pole P is connected to throw T1, that is the first state. In that case, we find that S1 and S2 are in the on state, the top 2 devices are in the on state. So, it also means that S3 and S4, the bottom 2 devices are in the off state. S4 has to be off, S3 also has to be off. If S3 is not off, then there is a possibility that the pole may get connected to 0, right. Similarly, when pole P is connected to throw T2, then S2 and S3 should be on, then S2 and S3 should be on. So, depending on the direction of load current, if the load current flows in this direction, the conduction will be between through this diode and through this transistor. On the other hand, as I mentioned before, if the load current is in the opposite direction, then it will flow through this transistor and here and into the DC bus midpoint. So, in such situations S2 and S3 will be on and S1 and S4 will be off. This will prevent the pole from getting connected to either the top throw or the bottom throw. Now, let us say pole P and T3 are connected together. That basically means the bottom 2 switches S3 and S4 are now on and the top 2 S1 and S2 are off. So, whenever you see S1 is on, you see S3 is off. Here you see S3 is on, S1 is off. Here again you see S3 is on and I am sorry, this should be off, there is a mistake here. So, this should be off, this should be off. So, S3 is on and S1 is off. So, S1 and S3 are complementary, S1 and S3 are switched in a complementary fashion. When S1 is on, S3 will be off and vice versa. Similarly, let us say we have S2 and S4. Whenever you find S2 is on, when will S2 be on? S2 will be on whenever you need to connect the pole to the top throw or to the middle throw. Whenever S2 is on, S4 will be off. When should S4 be on? S4 should be on when pole P is connected to the bottom throw. S2 should be on whenever the pole P has to be connected to the top throw or the middle throw. S4 should be on whenever it should be connected to the pole should be connected to the bottom throw. You see that they are mutually exclusive. So, S2 and S4 are complementary. Similarly, S1 and S3. S1 should be on only when the pole P is connected to the top throw. S3 should be on whenever the pole P has to be connected to the middle throw or to the bottom throw. So, S1 and S3 are complementary. Similarly, S2 and S4 are complementary. So, these are certain things we see now. In a 2-level inverter, we had only 2 transistors. So, they need gating signals and they are switched in a complementary fashion. So, effectively you needed only one independent gating signal. How about a 3-level inverter? In 3-level inverter, you need 2 gating signals, maybe for S1 and S2 or S1 and S4. So, S3 can be generated as the complement of S1 and S2 or S4 can be generated as the complement of the other. So, you need 2 different gating signals now, right. Now, we have not really framed we come up with a proper framework for calculating losses, which we will do it much later, but nevertheless we have some idea of losses. Let us try and see how the losses will be different in different devices, etc. If you take an earlier 2-level inverter, let us go back to one of the 2-level inverter. Now, this is a 2-level inverter now. In this, can we say that the losses in all the 3 legs will be equal? Yes. Why? Because we will be controlling them we assume all balanced conditions. There is a DC bus voltage and the load is balanced and we are controlling it in a balanced fashion. So, all the 3 legs will have equal losses, and the loss in every leg is due to both the top and the bottom device. And the top you have a transistor as well as diode and so on, and the losses can be split into either conduction or switching loss. So, the conditions are identical now. So, if a particular phase has a peak current now, the next phase will see the peak current some another 120 degrees later, and the third phase will see the peak yet another 120 degrees later. So, they are in a balanced condition, and therefore, they get heated to the equal this thing. There are some modulating methods which will lead an unequal loading of top and bottom, as we will see sometime when we are looking at this bus clamping PWM or discontinuous PWM. But we are by and large use such modulation methods which load the top and the bottom equally. So, all of them will be loaded to an equal extent. So, if the top transistor conducts for certain length of time, the bottom transistor will also conduct for an equal length of time. So, and again the total losses will kind of be equal between the two. Basically it is because of the symmetries. As long as you have symmetries between the 3 phases and every phase is half wave symmetric, there is some symmetry between the positive half cycle and the negative half cycle, the top and the bottom devices they also will have equal losses now. But the situation is a little different when you go to a multi-level inverter. Let us see how. Now, in this situation, let us just consider S1 and S2. When will S1 be on? S1 will be on whenever you have to connect the pole P to the top throw T1. This alone is a situation when S1 has to be on. When should S2 be on? S2 needs to be on whenever pole P is connected to the throw T1 or pole P to the throw T2. So, naturally S2 is on for longer duration than S1. So, whenever pole P is connected to throw T1, S1 is conducting and the transistor S2 could also be conducting. Well, it could be the diodes too, the corresponding diodes might also be conducting. But whenever pole P is not connected to throw T1, neither the transistor S1 or the corresponding diode will be conducting. But when pole P is connected to throw T2, half the time roughly transistor S2 or its transistor S2 will conduct, or for another half the time transistor S3 will conduct. So, S2 can conduct, it does conduct whenever pole P is connected to throw T1, and it also conducts part of the time whenever pole P is connected to throw T2, depending on the load direction. If the load direction is as indicated by the green line, S2 conducts now. So, what can we say? S2 is going to conduct for longer. So, its conduction loss is certainly higher now. So, the same argument can be made out between S3 and S4. So, you can see that the losses in S2 and S3 are likely to be a little higher than the losses in the other 2 extreme devices now. So, this is something that we can make out in a fairly qualitative fashion. So, we will evaluate losses particularly in the case of a 2-level inverter much later in this course, and that will also give us a necessary background to actually evaluate losses in a 3-level inverter. Now, we are just trying to see qualitatively how these things are affecting now. So, you would normally find that the middle 2 devices probably suffer a greater amount of loss. That is what you should expect at this point of time now. What I want to say is, this is not the only way a 3-level inverter can be realized. What do I mean by 3-level inverter? I have this pole which I call as R, which is same as the R phase terminal, and that pole, there is a voltage at that pole V at R measured with respect to O being the DC bus midpoint. Now, a 3-level inverter can produce value of VRO which is either plus VDC by 2 or minus VDC by 2, as in the case of a 2-level inverter, and also 0 and also 0. So, this is how it is different now. Can we have other possibilities other than what we have come up with as a 3-level neutral point clamp inverter, which can give you these values of VRO being 0 also in addition to plus or minus 0.5 VDC. That is what we are going to see. One alternative that we can think of is flying capacitor inverter, which we come to here now. Before that, let us just see, let us go to some higher levels of multi-level inverter now. So, this is called a 4-level inverter. It is called a 4-level inverter because you have 4 different potentials available here. There are 4 different nodes, 4 different potentials available, and then you have 4 different throws. You have 1, 2, 3, 4. So, it is a single pole 4 throw switch and the 4 throws are connected to 4 different potentials. So, here your VRO, O being the midpoint which is not indicated explicitly here, O is really the midpoint which is really the average of the two extreme potentials. If you look at your VRO, it can be plus or minus VDC by 2. If R is connected to the top throw or bottom throw, you get plus VDC by 2 minus VDC by 2 as in a 2 level inverter. In addition to that, you also get potentials plus or minus VDC by 6. If R is connected to the second throw or the third throw, you get potentials plus VDC by 6 or minus VDC by 6 respectively. So, this is a 4 level inverter. Your pole voltage has 4 different levels now. Similarly, you can also have a 5 level inverter. In this case, you see that there are 5 different potentials 1, 2, 3, 4 and 5. These are connected to 5 different throws and you have a single pole 5 throw switch. You have a single pole 5 throw switch here. Here you have a 4 throw switch, here you have 5 throw switch now. So, here you have your VRO equal to several values. It is equal to plus or minus VDC by 2 as you would normally have in a 2 level inverter. In addition, VRO can take values of plus or minus VDC by 4 also if it is connected here or there, and it of course, it can also take the value 0. So, it can take 5 different values plus or minus VDC by 2, plus or minus VDC by 4 and 0. So, you call this as a 5 level inverter now. So, how do you realize these 4 level and 5 level inverters is a question. So, it is actually a single pole 4 throw switch and you can come by realizing it one by one, follow the same steps that we followed in a single pole triple throw switch now. So, what you will now get is, you see that there are earlier we had 4 transistors here, now we have 2 transistors more at the extreme ends. This is what we have. And also you have, instead of 2 different sets of series capacitors, you have 3 sets of capacitors and the capacitors carry a voltage equal to VDC by 3. So, 3 sets of capacitors each support a voltage of VDC by 3, together it adds to the total DC bus voltage VDC. So, these points 1, 2, 3 and 4 points are connected now. So, the middle 2 points particularly plus VDC by 6 and minus VDC by 6 are connected through a set of diodes either to one of these intermediate points, these intermediate points here, they are connected there, and so they then through the other transistor or the diode they can conduct to R for example. So, you have a single pole 4 throw switch realized here. For example, if you say R is conducting in a particular direction, if let us say the current is flowing in this particular direction and let us say the pole has been connected to VDC by 6 this throw, then the current can flow through this diode, through this transistor and through this transistor and can flow out now. Let us take another example, that is the current is flowing in the opposite direction now, in the opposite direction and it is connected to the same, the pole is connected to the same throw. In such a scenario, it will connect through the bottom transistor and it will go up through these 2 diodes and go there. So, that is how the direction of current flow is. Similarly, you can see the situation, you can study the situation where the pole is connected to the other throw which is equal to minus VDC by 6. So, every time you increase that, some 2 more transistors get increased and the voltage level gets increased by 1 more. You have one additional set of series connected capacitor. In case of a 3 level inverter, you had 2 sets of capacitors in series. In case of a 4 level, you have 3 of them in series. If you go to 5 level, you will have 4 of them in series now. So, then you have more number of transistors and you also have diodes which will go and clamp them or connect them to the appropriate nodes. So, this is how you have a 4 level inverter. If you want to go for a 5 level inverter, it just goes up like this now. So, this is very popular, all these are diode clamped inverters. So, they are you are use diode for clamping. The alternative option that I was trying to say to realize VRO is of different values. This is also an inverter where I can realize VRO equal to plus or minus VDC by 2 as in the case of a 2 level inverter and also 0. This is another thing. What do I do here? I used charge capacitors. So, there are 2 sets of capacitors which are charged in series to voltages, I mean they are charged to voltage levels of VDC by 2. These two sets of capacitors are in series now, they are supported, they are fed from some voltage source here of plus minus as I have indicated here now. So, these two are firmly connected, their terminals are firmly connected to a voltage source, let us say. Now, we have yet another capacitor, the same value C, let us call these values as C, and it is also charged to plus 0.5 VDC with polarity as indicated here now. So, what I can do is if I add this, if I use a switch like this S1 and close this switch, then the potential at this point, this is the potential at this point will be equal to 0 if this switch is closed. So, alternatively, if let us say this switch is closed, this closed, then the potential here would be 0, the potential there would be 0. So, what we are trying to do is we are trying to realize multiple voltage levels by connecting charged capacitors in series. So, we have one charged capacitor of 0.5 VDC, we are trying to connect this in series now. So, this 0, it can be taken in by using a single pole double throw switch as indicated here. Now, let us say R needs to be connected to just the positive bus. All that you need is R has to be connected to the top throw as here, and S1 is closed, excuse me, right. If R has to be connected to the bottom throw, then what you need to do is R can be connected to T2 here and S2 can be closed, then that will connect it to the bottom throw. If R has to be to the negative DC bus, if R has to be connected to the DC bus midpoint, you are not connecting it to the DC bus midpoint exactly, but what you are trying to do is you are doing a series connection like that. You are closing S1 and so that the potential here is 0 and you can close this switch. So, this combination, this switch closed means this midpoint is equal to 0 and you can put your this single pole double throw switch can be connected to the bottom throw. So, this gives you a potential equal to 0. You can get this potential equal to 0 in another way also as indicated by the red one. This switch S2 can be closed, of course, S1 has to be opened now, S2 is closed. So, in that case what happens, the potential here is 0. So, this is kept in the on condition, this switch is kept in the on condition. So, you can apply 0. So, if R has to be connected to the positive DC bus, there is only one way of doing, the pole has to be connected to the top throw and S1 has to be closed, of course, S2 has to be opened. If pole P has to be connected to the negative DC bus, I mean the R phase terminal, again it is unique, pole has to connect to the bottom throw and S2 has to be closed. But if the pole has to be connected to the DC bus midpoint or should be connected to the DC bus neutral, a potential equal to the DC bus neutral, there are two different ways. For VRO is equal to 0. You can connect this pole to the top throw and the bottom switch S2 can be on here, or alternatively switch S1 can be on and this pole P can be connected to the throw T2. So, these are two different ways by which you can realize this. So, here also you are getting VRO is equal to 0 in two different ways now. So, you are getting VRO is equal to 0 just in the case of a 3 level inverter, that is possible now in two different ways. Now, we have to see how do we realize this switch. So, if you have such switches, you can it is possible to produce VRO is equal to plus or minus VDC by 2 and also VRO is equal to 0. So, it is the same as or equivalent to a 3 level inverter, you are able to apply 3 different potentials at the pole now. So, how do we realize the switches? That is the first question now. Let us first look at how S1 and S2 can be realized. Now, what is going to be the direction of current flow? It is an AC load. So, current can be flowing in either direction. So, if you consider switch S1, S1 is closed, S2 has to be open, right, because if you see the series potential here is VDC, whereas the potential here is only VDC by 2. Therefore, closing S1 and S2 is not possible. If S1 is closed, S2 has to be open or vice versa, but at least one of them has to be closed, otherwise the DC bus capacitors will be totally isolated from the pole voltage. So, one of them will have to be closed to make a connection now. So, either S1 is closed or S2 is closed now. So, let us consider the situation S1 is closed. If S1 is closed, then your conduction direction of conduction depends on the load current. It can be conducting either from the left to right or right to left, as I have shown here now. So, the switch S1 has to be a bidirectional current carrying switch now. How about S2 correspondingly? Now, what we have done is S2, this side potential is equal to 0, whereas this side potential is equal to negative. So, S2 is actually blocking a potential which is plus on this side and minus on this side, and the potential is equal to VDC by 2. The same scenario, if you consider that S2 is on, if S2 is on, this will be conducting in one of the two directions depending on the load current, and here it will be blocking a potential with such polarity. S1 will be blocking potential with this polarity now, because this is closed, right. Here the potential is equal to that of the positive terminal, this side the potential is equal to that of the DC bus midpoint. So, the potential difference is VDC by 2 with polarity as indicated now. So, this is what perfectly fits our bill. This is what fits our bill. So, what you need is you get a bidirectional current carrying switch and a voltage blocking capability as shown here. The same way for S2. So, you just basically use an IGBT with an anti-parallel diode that serves the purpose for S1 and S2 now. Now, what we need to do is we need to look at how to realize this single pole double throw switch. So, as we said before, the current is bidirectional. Therefore, if the pole is connected to the top throw, the devices between the pole and top throw or whatever switch comes between there has to have a bidirectional current carrying capability. So, when that is there, what happens here is this potential is now connected to the top throw and therefore, to the positive terminal of this capacitor. So, this comes here and this connects to the negative terminal of the capacitor. So, this is equal to minus, and the potential difference is the same as what you have here. This capacitor voltage comes across the pole and the throw. So, this is what you get by having two transistors like this. You have a transistor and an anti-parallel diode, so that they have a bidirectional current carrying capability. Now, the bottom transistor can block a potential like this now. On the other hand, let us say you have pole connected to throw T2. If pole is connected to throw T2, then this has to be bidirectional current P and T2. Between P and T2, you need a bidirectional current carrying capability. So, that is what you have now. So, when pole is connected to throw T2, then the top throw is positive now with respect to the bottom throw, and it is blocking a potential equal to VDC by 2. It is blocking a potential equal to VDC by 2. So, this is what you have now. So, a single pole double throw switch can be realized. It is just the same as what we had in a, let us say, a voltage source inverter or so. So, this is how you realize this, and we put together all the realizations. S1 and S2 are basically IGBTs with anti-parallel diodes, and the single pole double throw switch is basically a leg like this, S3 and S4 now. This is one leg of a flying capacitor inverter. You can have yet another leg, and then it two legs to make a single phase inverter. You can have three such legs to make a three phase inverter now. So, now the rules are very clear. S1 and S2 are complementary. S1 is equal to S2 bar. If both are open, there is no power. The DC side is totally isolated from the load side now. It does not function. The inverter is not functioning. There is no power flow there. If both are on, you are shorting capacitors charged to VDC by another set of capacitors charged to VDC by 2, which you can't be doing. So, S1 and either if S1 is on or S2 is on, the other one should be off now. So, S1 and S2 are complementary, and of course, S3 S4 basically it is actually a realization of single pole double throw switch. Therefore, you also have S3 is equal to S4 bar. This is how you operate the switch now. So, here again you need two gating signals, let me say S1 and S3. From S1 you can generate S2, from S3 you can generate S4, and you have your VRO is equal to various values. VRO can be equal to plus 0.5 VDC. If S1 and S3 are on, if S1 and S3 are on, then your VRO will be equal to plus VDC by 2. If your S2 and S4 are on, then your VRO will be equal to minus VDC by 2. The other hand, if you have your S1 and S4 on, if you have S1 and S4 are on, if you have S1 and S4 are on, then what happens is you get 0, this potential is now effectively 0, and so VRO is equal to 0. The same thing can be realized by having S2 and S3 also on. Now, let us say the current can actually be bidirectional. So, here let us say you are having VRO is equal to 0. Now, let us say this has been achieved by having these two switches S1 and S4 on. So, the current conduction will be like this. This is how the current will be conducting. Now, let us say you want VRO is equal to 0 and the same direction of conduction, but by S2 and S3 are on now. So, what you will have is you will have sorry. So, this would be the direction of current flow. This you ignore that, let me erase with a eraser. Okay. So, what you really have is, so the current actually flows in this direction through the transistor and it flows out. So, in one, if for one set of switches the capacitor charges and the other set it discharges. So, what we need to do is we will actually apply VRO in one fashion and the other fashion alternatively to make sure that the capacitor does not get discharged. And you see that this capacitor, its terminals are not connected to any firm potential, whereas this capacitor's terminals are connected to firm potential. These two are actually connected to some DC supply. So, they are connected to firm potentials, and this is just a series connection of capacitors now. And if you look at here, what do we have? Neither of these two terminals are connected to any firm potentials, they are actually connected to switches now. Therefore, you get the name flying capacitor. Basically, the capacitor's terminals are not connected to firm potentials now, it is floating or it is flying capacitor inverter now. So, you have a unique way of connecting the pole to the positive DC bus or the negative bus. But if you look at the intermediate potential, namely VRO is equal to 0, you have multiple ways of doing this, and these multiple ways of doing this help you maintain the charge on the capacitor now. In flying capacitor, this is certainly a challenge for you to first have the capacitors charged to this voltage level and continue to maintain that the capacitors remain charged at these voltage levels now. So, it has to be modulated and it has to be controlled in an appropriate fashion that these capacitor voltages are reasonably at 0.5 VDC, that is what we have been trying to say now. So, there was an additional point that we really had to make about a 3-level inverter now. If we say in a 3-level inverter, we see that the current here actually flows into the DC bus neutral. In a 2-level inverter, where does the current flow? The current, only the ripple current here flows. One of the early slides, if you look at an early slide where we looked at this, or maybe we can take this here. So, you will have some current and what flows through is will only be a ripple here, we will call it as some I tilde or so. This is some IDC, it is a sum of these two is going to flow here. It is only a ripple that flows through that. Now, what happens? There is no actual DC current or anything flows through that. In the case of a 3-level inverter, because you are connecting it to the midpoint, the load current sometimes flows through the DC bus neutral. Because of this, you can have a situation where the top DC bus is charged or discharged in a particular fashion now. Let us say you have this like this now. If the load, if your poles are connected only to the top throw or the bottom throw, then the load current has, let me say that the top two are on now. So, they are conducting like this and there is a current flowing like this, and then this is how the current flows. So, it flows out. So, this is how the current is flowing. So, there is no current, load current really flowing through the capacitors. On the other hand, let us say you have A connected to the midpoint, A connected to midpoint, that is this O. So, in that case, for a particular direction of current, if I look at, current can be flowing in this direction. And let us say B is connected to the bottom throw. In that case, current is flowing like this through the two transistors and flowing back here. So, you see that there is certain amount of current which flows through those DC bus capacitors. The load current is now flowing through the DC bus capacitors. So, there is going to be a substantial charging and discharging now. The advantage of a 3 level converter itself lies in the fact that it gives you a better waveform quality, that is basically you are able to connect the pole to the midpoint. That also provides you a disadvantage, namely the DC bus is going to be the balance could be lost. You need good modulation and control methods to really come up with that. Okay, so that is something we will look at when we are doing a modulation of DC bus this thing. Now, let us just quickly go towards the end. So, this is what one leg of a flying capacitor converter that we had. So, if you want to go increase the number of levels, how do you do that? I just leave that to you. What you basically need is just as an exercise, you need more switches and you will need more stages of capacitors. How many stages, how many switches, etc., I would leave them to you. So, it is possible for you to once again come up like a 3 level, 4 level, 5 level, etc. And to quickly summarize, this neutral point clamp or diode clamp multi-level inverter is what we have been discussing extensively and what we will use in this course. We also discussed flying capacitor now. This multi-cell is about using two single phase inverters for one leg. A single phase inverter can produce some voltage output which is equal to 0 or the input voltage or the negative of the input voltage. So, you can have two of them connect them in cascade. So, two of them can in series and connection can give you some number of voltage levels. So, it is also possible to realize multi-level inverters using several single phase inverters, two single phase inverters for example in one leg. So, those are the three important ways, but our focus will be primarily on neutral point clamped in this course now. So, I thank you very much for your attention, and in the subsequent classes we will start discussing more about modulation. Before we go into modulation, we will quickly look at the various applications of voltage source converters in the next lecture. Thank you very much.